Okay. Thank you. So let's basically continue today where we left off yesterday. So remember that yesterday we talked about neutrino oscillations in matter, and we introduced the process of coherent forward scattering, which is a scattering process in which no momentum is exchanged. So the quantum state of the final state particles is identical to the quantum state of the initial particles. And we had argued that even though hard neutrino scattering is all but negligible when neutrinos travel through matter, this coherent forward scattering process may not be negligible because, since there is no change in the quantum state, there's in principle no way to determine which of the many background particles the neutrino has interacted with. So the different amplitudes are summed up coherently, which means that the rate for such a process is proportional to the number of scattering targets squared, rather than just the number of scattering targets. And this is a huge enhancement that can make these effects observable. Now, the processes that we have in mind specifically is either neutral current scattering of a neutrino on an electron, proton, or neutron, or charged current scattering of an electron neutrino on an electron. And we had argued that, of course, this process here on the right is only possible for electron neutrinos, whereas the one on the left is possible for all neutrino flavors. So what we're going to do next is we're going to formalize this a little more and turn this into equations. So let's look in particular at the process on the right. So the process of coherent forward scattering of electron neutrinos on electrons. The effective Hamiltonian for this, or the effective Lagrangian, if you wish, can be written in the following way. So it's a low energy process. So we're going to work with the Fermi effective theory of weak interactions. So the W boson can be integrated out. And the interaction that's relevant here is G Fermi divided by square root 2 E bar gamma mu times 1 minus gamma 5 E times, sorry, not E, nu E. It's a charged current interaction after all. And then this is coupled to another fermionic current, nu E bar gamma mu 1 minus gamma 5 times E. Now what we can do to this, we can apply a Firth transformation. And what the Firth transformation does is it basically allows us to write this product of currents in terms of a product of two currents where the fields are ordered in a different way, namely like this: GF over square root 2 times E bar gamma mu 1 minus gamma 5 E times nu E bar gamma mu 1 minus gamma 5 times nu E. Oh, and I realize that I put the mu here in the wrong place. This should, of course, always be one upper index, one lower index. Okay.
Joachim?
Yeah.
There is a question on the chat by Aman. Can the right process, sorry, let me read it out real quick. Can the right process be occurred with a muon and muon neutrino?
No, it cannot, because there are no muons in the background matter. So ordinary matter has only electrons in it. So for this to happen on a muon neutrino, well, the electron would need to be replaced by a muon, but there are no muons available for the initial state. And if we were to consider, for instance, the scattering nu E to E and mu to nu mu, then it would no longer be coherent forward scattering, because then even though the momentum doesn't change, the flavor would change. And coherent forward scattering means that none of the quantum numbers changes, including flavor quantum numbers.
Thank you. And Gabriela is asking, what is the dependence of the coherent scattering on neutrinos' energy?
We will come to the energy dependence later. So it's a very good question. The energy dependence is indeed quite important, but we'll see that at the end of the calculation. So I ask you to be a little patient. We'll get to that in a moment.
Thank you.
Okay. Now, the background material that the neutrinos are propagating through can be treated as more or less static. So we are going to treat the electron fields here as a static background. So in other words, we're going to treat them as a classical field, and we're going to replace them by their expectation value. So we treat E as a fixed background field. Sorry. So we take the expectation value. So in other words, we are interested in the expectation value of this effective operator, which is defined as G Fermi divided by square root 2 times, well, the expectation value of the first current here, expectation value E bar gamma mu 1 minus gamma 5 E. And the second current, the neutrino current, is left unchanged. Now we need to evaluate this expectation value. So how do we do this? I won't have time here to go through this in all its gory detail. The derivation should be in the lecture notes, though. Basically, what you need to do is you expand the E field here as a Fourier series. So you write the field as an integral over all momentum modes. And then a particle creation operator times a complex exponential factor plus a particle annihilation operator times a complex exponential. And you contract these creation and annihilation operators with the creation and annihilation operators that create the external state. So the external state, is just we discussed this yesterday, a quantum state is just a creation operator applied to the vacuum. You do this, and what you will find is that this whole expectation value is essentially proportional to the electron number density if mu equals 0, and it's 0 if mu is not equal to 0. Because for the spatial components of this current here are essentially the net momentum of the background matter. And because we assume the background matter is at rest, the net momentum is 0. Also, the terms involving a gamma 5 here do not contribute because we assume that the background has a net spin of 0. So we are traveling, the neutrinos are traveling through unpolarized matter. So, let's write this down here. So this is Ne for mu equals 0. And it's 0 for mu equal to 1, 2, and 3. And as I said, I won't be able to go through the detailed derivation, but it's in the lecture notes, and it essentially amounts to expanding the field operators in terms of creation and annihilation operators, writing the external state as a distribution of particles with some momentum distribution, and then doing the contraction of the creation and annihilation operators appearing in the external states with the creation and annihilation operators appearing in the field operators. And the end result is that we just find an integral over the momentum distribution of the external particles. And this integral, well, the integral over the momentum distribution, or the integral of the phase space distribution over momenta, is just the number density. So nevertheless, that's a pretty crucial result here, because now this whole Hamiltonian here takes a relatively simple, form. It's just square root 2 G Fermi times Ne times nu E left bar, gamma 0, nu E left. Remember, this is only non-zero for mu equals 0, so only the mu equals 0 contributes here. And this quantity here, this square root 2 GF times NE, this is what we often call VCC. And that's the charged current Mikheyev Smirnov-Wolfenstein potential, or MSW potential. Because this term that we have derived now, it has exactly the form of a potential term. So for instance, the coupling of a particle to a static electric or magnetic field looks pretty similar when written out in the language of Hamiltonians and Lagrangians. There is a fermionic current coupled to some constant value. And here this constant is coming from coherent forward scattering. Okay, now a similar derivation can be done also for the neutral current operator. So for this diagram here, where a neutrino scatters via Z exchange. And this gives us a neutral current potential, which is -1/2 times square root 2 G Fermi times the number density of neutrons in the background matter. Okay. Now, what do we do with these potentials? Remember that when we computed oscillation probabilities, the interference terms were arising from complex phase factors of the form e to the I times momentum times distance. So in the derivation of oscillation probabilities, in the derivation of P nu alpha to nu beta, we had factors of the form e to the I times P times L. This is where the momentum dependence of neutrinos came in. And this is also where now the potential will modify things. So consider this phase phi, which I define as just to mean the momentum times L. So the momentum is square root of the kinetic energy squared, square root of the total energy squared minus the mass squared. So now in the presence of a potential, that can be written as the Hamiltonian minus the potential, you'll see in a moment why I put little hats on top of here, minus m squared. So here, H is, well, of course, the Hamiltonian. We are working in a two-flavor system, so this Hamiltonian is a 2x2 matrix. I'm going to write it out explicitly in a moment. This here are the MSW potentials. That's also a 2x2 matrix. We are also going to write this out explicitly in a moment, but you can already guess why it's a 2x2 matrix. And that's because the potential is different for different neutrino flavors, right? One of our processes, namely the charged current one, existed only for electron neutrinos, not for other neutrino flavors. And finally, this here is the 2x2 mass matrix. Once again, in reality, this should, of course, be 3x3 matrices, but to keep things simple here, I'm working in a two-flavor approximation.
Joachim, there's another question by Nele.
Please go ahead.
So I read it out. Why do you only have NN, so the nucleon density in the neutral current potential and not the electron or proton densities?
It turns out that the contributions from electrons and protons cancel exactly. They are the same per particle. And because there's equal numbers of electrons and protons in neutral matter, they exactly cancel. So in the end, we're only sensitive to the neutron density.
Thank you.
Okay. Now, before we proceed, we can make one approximation here. Namely, we can use that M and V are much, much smaller than the kinetic energy of the neutrinos. So we use that V and M are small. And we do a Taylor expansion, which then leads to H minus M square over 2H minus V hat. So remember that these are all matrices. So when I write here M hat square divided by H, this means just taking and multiplying by the inverse of the matrix H. So this is now the new phase factor appearing in neutrino in the calculation of the neutrino oscillation probability. Now, in order to make progress, we need to determine once again where the eigenvalues of this matrix are. For oscillations in vacuum, we only had H minus M square over 2H, and we then had to diagonalize essentially the mass matrix. Now we have also this matrix V here. And so the diagonalization problem is a little more complicated. So we need to diagonalize H minus M square over 2H minus V hat. That's equal to the neutrino energy times the unit matrix minus the contribution that we also had in vacuum, which is a mixing matrix times M1 square over 2E, M2 square over 2E, U dagger. And now we still have the matrix V, which is minus VCC plus VNC and VNC. So this now also defines explicitly what this matrix V hat is. And it's pretty straightforward to understand. The neutral current potential affects both neutrino flavors. The charged current potential affects only electron neutrinos, so it only appears in the upper left-hand component. I've written this all still in the flavor basis here. So the potential matrix is diagonal in this matrix, whereas the contribution from the masses here is off diagonal, right? The U and U dagger matrices basically do the transformation between the mass and flavor basis. So I've written down the Hamiltonian in the mass basis here in the middle, and I'm multiplying it from the left and from the right with the PMNS matrix in order to go to the flavor basis. So overall, this is now the Hamiltonian in the flavor basis. The mass basis is now not a good basis anymore, because if I went to the mass basis, then, well, I would be diagonal in the mass basis, but I would no longer be diagonal in the energy basis. So now the states of definite mass do no longer have definite energy either. So now we have three sets of states. We have the flavor eigenstates, we have the mass eigenstates, and we have what we call the matter eigenstates. And those are the states in which this whole Hamiltonian is diagonal. Okay, now doing the actual diagonalization is maybe a page of algebra or so. And I encourage you to do this during the self-study and exercise time. Here, I'm going to give you directly the result, and I'm going to discuss it, of course. So the result is that let's see, the effective mixing angle, sine squared 2 theta effective. So the mixing angle of the rotation matrix that diagonalizes the Hamiltonian has the following structure: sine 2 theta. So theta is the mixing angle in vacuum. Theta effective is the effective mixing angle in matter, times delta m square over 2e, divided by a big square root, which goes over the following: square root 2 GF NE, so just the charge current potential, minus delta M square over 2E times cosine 2 theta squared plus delta M square over 2E squared times sine square 2 theta. And we need to close the square root over here. And also the eigenvalues can be written once again in terms of an effective delta M square. So delta M effective square divided by 2E. So the eigenvalues are, of course, an M1 effective and an M2 effective. But for oscillations, once again, the only thing that matters is this delta M effective square over 2E. So I'm going to give you that quantity right away. And that is essentially just this big square root here. So square root 2 GF NE minus delta M square over 2E cosine 2 theta squared plus delta M square over 2E squared times sine square 2 theta. So let's look in particular at the mixing angle here, because the mixing angle, remember, is what determines the oscillation amplitude. So you can see that obviously it's in some way it depends obviously on the vacuum mixing angle, but it has this denominator here, which has quite an interesting structure. In particular, notice that the first term here, which is a difference between something that contains essentially the oscillation frequency and the charged current matter potential, this term can in principle go to 0. If I tune the matter potential against the energy in the right way, then I can make this first term here go to 0. And in this case, only the second term survives, but the square root of the second term is identical to the term on top here. So at this particular point where the term in parentheses here goes to 0, sine square 2 theta effective is equal to 1. So it's maximal. And this is independent of what the vacuum mixing angle theta was. And that's one of the most crucial aspects of neutrino oscillations in matter. And that's what's called the MSW resonance. So MSW stands for Mikheyev, Smirnov, and Wolfenstein. So at the MSW resonance, which is defined by delta M square over 2E times cosine 2 theta, is equal to square root 2 GF times NE. The effective mixing angle is maximal. The effective mixing angle is maximal. And this also answers one of the questions that I was asked earlier about the energy dependence. Here is one point where the energy dependence is really, really crucial. So in terms of, let's see if I have a nice picture of what this looks like. A moment, let's see if this is in here. Yeah, let me show you one slide. So can I, in principle, I should be able to share two things simultaneously. You should now be able to see my PDF viewer, right?
Yes, we do.
So these two plots here, they show the oscillation probability, in this case for mu to E transitions, as a function of energy. This plot was, of course, done in a full 3-flavor framework, so there's a lot going on here. So let's discuss this. The top panel here is at a relatively short baseline. The bottom panel is at a much, much larger baseline. So what you see here first, let's first look at the top panel, which is a bit easier to understand. At very large energies, there are no oscillations because the oscillation frequency is proportional to the inverse of energy. So at these large energies, oscillation simply did not have time to develop yet over a distance of just 800 kilometers. Then you see the first oscillation maximum here at an energy of a few GeV, and then other oscillation maxima follow. It's not a pure sine curve, but it's actually a superposition of short wavelength and long wavelength oscillations, because we are in a three flavor system. So there's two delta M squares that matter here. One of them controls the frequency of the short oscillations. The other one controls the frequency of the large oscillations. This appearance of two oscillation frequencies is much more evident here in the bottom panel, where we are now at larger baselines, so oscillations have had more time to develop. This means in particular that the first oscillation maximum sits here already at maybe 20 GeV. And then among the other oscillation maxima, we see very nicely this superposition of two different oscillation frequencies. The small wiggles here are driven by the large delta M square, delta M31 square. The long wiggles are driven by the smaller delta M square, delta M21 square. So let's now compare the red to the black curve. The black one is for oscillations in vacuum. The red one is for oscillations in matter. And this is where now the big difference comes in. Not so much at the short baseline of 800 kilometers, but at the large baseline of 10,000 kilometers. Here you see the MSW resonance. So here in a region where the oscillation amplitude in vacuum is extremely small, the oscillation amplitude in matter becomes pretty large. And this happens precisely here at the energy of the MSW resonance, which is indicated by this vertical dashed line here. You see that also at lower energies, the presence of matter leads to some substantial deviations between oscillations with and without matter. But the most striking feature is really this resonance up here at energies of several GeV. Note that in principle, this resonance is also present in the top plot, right? The energy at which the resonance happens is independent of the baseline. However, in the top plot, the oscillation simply did not have time to develop yet. So even though there would be a maximal oscillation amplitude here, if the oscillation phase is still too small, you still don't see oscillations. Okay.
Joachim, maybe this is a good time for two questions from the students.
Oh yeah, I see something going on in the chat, yeah.
Yeah, so Jamie is asking, so do this formula also work under ultra high densities or temperature conditions, for example, in supernovae or neutron stars?
Let's say the basic ansatz still works. The problem in those environments, so as long as it's only ordinary matter, the density doesn't really make such a big difference, and that still works even in supernovae. The problem is that in a supernova, the neutrinos are so dense that the neutrino feels the presence of the other neutrinos. So in addition to the two diagrams that I've shown here, neutral current scattering on electrons, protons, and neutrons, and charge current scattering on electrons, there are now also processes where neutrinos scatter on neutrinos. Those are no longer negligible in a supernova. And these can be included in exactly the same way, but now there's two neutrino currents appearing in here. And because the neutrino ensemble is highly dynamic inside a supernova, and it's of course affected by MSW effects, we can no longer make this mean field approximation. So we can no longer simply take expectation values, but we really have to take into account the evolution of the neutrino ensemble in both currents appearing in this effective interaction here. And this makes the whole problem highly nonlinear and practically unsolvable. So great progress has been made on understanding of such systems in recent years, but one expert once told me, in this field, never trust any result that's older than 2 years, because it's just moving so fast, and we don't even have a particularly good qualitative understanding of what's going on. So even the qualitative understanding has changed quite significantly a couple of times over the past 2 decades or so, just because it's a highly dynamic system, and in order to fully solve it, you would need to run a simulation that is fully three-dimensional, so propagates neutrinos in 3 dimensions, and on top of that also takes into account the impact that neutrino oscillations have on the supernova. So you basically need to simultaneously evolve a neutrino ensemble in its full glory, 3 flavors, 3 dimensions, and do all of that together with the magnetohydrodynamics that control the supernova explosion. And you may have heard how difficult that alone already is. So I would say it's a very important problem, but it's a problem that has not been fully solved yet. But the basic ansatz is the same as the one we've used here.
Thank you. And then there's a question by Simone. If the matter density is not constant, can we diagonalize locally in such way?
Locally, we can diagonalize in such a way. However, in that case, that is not the full answer. Because what happens, for instance, one very important situation where this is the case is neutrinos traveling out of the sun or traveling out of the outer layers of a supernova. And there, the matter density, of course, changes from about 150 grams per cubic centimeter at the center of the sun to 0 outside the sun. And this is a very gradual and slow drop in density. And because it's so slow, the neutrino flavor conversion happens basically adiabatically. So at the very center of the sun, the matter density is so high that the mixing angle here is way above the MSW resonance, and essentially the mixing angle is pi over 2. When the mixing angle is pi over 2, this means that effectively the mass and flavor eigenstates are almost aligned with one another. So the electron neutrinos that are produced at the center of the sun are essentially simultaneously in a mass eigenstate, namely in the nu 2 mass eigenstate. And then what happens as the neutrinos travel out of the sun, I shouldn't have said the nu 2 mass eigenstate, the nu 2 meta eigenstate. Now, as they travel out of the sun, the relation of this nu 2 meta eigenstate to the flavor eigenstates change because this effective mixing angle changes. However, because the transition is so slow, the neutrinos essentially always track the nu 2 meta eigenstate. So they stay in the nu 2 meta eigenstate all the way until they reach vacuum. So they end up in vacuum being essentially in the nu 2 mass eigenstate. And that's quite different from a normal oscillatory phenomenon. There's no real oscillations going on here. So when we talk about solar neutrino oscillations, that's to a large extent a misnomer. Most of the or let's say many of the solar neutrinos, namely those at higher energies, do not oscillate at all. They are produced in a meta eigenstate and they stay in that meta eigenstate and then travel to Earth essentially in a mass eigenstate. Well, and then they oscillate a bit once they enter the Earth because then the matter potential is again different, but essentially they are not oscillating. The lower energy solar neutrinos, they do oscillate because for them, so at low energy, this condition, the resonance condition, cannot be satisfied because the potential even at the core of the sun is not big enough. So the lower energy solar neutrinos basically oscillate as if they were traveling in vacuum. But it's a very good question, and indeed, oscillations of solar neutrinos are quite an important topic, and the formalism for that is also quite interesting and is based on what we've just derived here. But I fear we won't have time to really go through it today in all its mathematical detail.
I think you also had a couple of exercises on exactly this topic, right? That you submitted.
Yeah.
So before you continue, one last question by Eleonora. Does the resonance depend on the neutrino flavor?
Well, the resonance tells us how one flavor converts into the other. So in the 2 flavor picture that we've talked about here, we can't really say there's a dependence on flavor because there's only 2 flavors and the resonance controls the transition between those 2 flavors. In the 3 flavor case, it does. So in the 3 flavor case, there are 2 resonances, one corresponding to the smaller delta m square and one corresponding to the larger delta m square. And they behave somewhat differently in flavor space. In practice, all flavors feel both resonances. However, the detailed shape of the oscillation probability at the resonance is different for the different flavors in general.
Thank you.
Okay. So that was how far I wanted to go into the MSW resonance. I think it's now time that I switch from my handwritten notes to showing you some more slides. And let's do this by starting with the slides on the topics that we discussed already on Monday. So this may be also a good reminder. So let me quickly share this with you. Here. Okay, so remember on Monday, we discussed neutrino masses from a theoretical point of view. And so the question is, how do we measure neutrino masses? Well, one approach that we discussed is the kinematic one. Remember, we discussed that the spectrum of a nuclear beta decay around the endpoint depends on the neutrino mass. And so in order to measure this effect, we basically need a very, very precise spectrometer. And the KATRIN experiment in Karlsruhe, Germany is such a precise spectrometer. This drawing here is quite complicated. And in fact, the experiment is quite complicated. But conceptually, it's not so difficult to understand. It all starts here with a tritium source. So this is basically a container of a tritium gas, where the tritium gas is allowed to decay. The technological challenge here is that you don't want to put any material in the way of the outgoing electrons, because if they had to go through any material, they would be slowed down. So how do you build a container that doesn't have a boundary, but still contains the tritium inside? Well, and basically the way they achieve this is with a very ingenious pumping system. Then the electrons coming out are passed through a pre-spectrometer and then through the main spectrometer. And the way the spectrometer works is, well, there is a magnetic field, which forces the electrons to travel along the magnetic field lines. And there is an electric field, which slows them down. And the electric field is adjusted in such a way that only the electrons whose energy is nearly maximal, so which is very, very close to the endpoint of the spectrum, have enough energy to traverse the electric field. The others are stopped and lost inside this big vessel here. And then we basically do a counting experiment. We see how many electrons are detected above the threshold that we've set. And then by varying that threshold, one can map out the upper part of the spectrum. And finally, behind the spectrometer, of course, there needs to be a device that's actually able to register the electrons. So people often argue that KATRIN is going to be the last experiment of this type. And the reason for that is its sheer size. So it's just doesn't make sense anymore to make a spectrometer even bigger. So here you can see, for instance, the main spectrometer vessel. You see here a rather big ship, and this gives you an idea of the dimension of this thing. Here are some small people. And because it's so big, it had to undergo quite an interesting journey to reach its destination. So here's a map of Europe. This vessel was manufactured over here in a town called Deggendorf in southeastern Germany, and it was supposed to be deployed in Karlsruhe. So how do you get it there? It's so big, you can't go on a highway because it won't fit under the bridges. I think there was at some idea a proposal to transport it with a blip, so a Zeppelin airship. But the problem is that the company that operated that airship went bankrupt before the plan could be executed. So they had to do it by boat. Fortunately, Deggendorf is on the Danube River. So the thing was loaded onto a boat, then went all the way down the Danube River into the Black Sea, through the Bosporus, through the Mediterranean, around Sicily, through the Strait of Gibraltar, around Spain, around France, and back up the Rhine until it reached a small town close to Karlsruhe, about 15 kilometers from Karlsruhe. And then it had only to do these 15 kilometers by road. And this is what the road trip looked like. And here you can basically see you can't make the spectrometer any bigger without tearing down the houses here. So this is the small village where it was unloaded from the ship and then was transported through this tiny village with a few centimeters of leeway on either side. Here's what it looks like now that it's been installed. Of course, the lighting makes a big impact here. You see the coils around here that control the fields. And here you see the shiny silvery vessel. And this is what it looks like from the inside. Here there is still some scaffolding inside to assist the installations, but this is what the vessel looked at from the inside. Sorry. Okay, and here is the result from KATRIN. The vertical axis is the count rate, the horizontal axis is the neutrino energy. And you basically see here the high energy part of the spectrum, which then levels out to 0 at energies above the Q value of the decay. And the current result from KATRIN is that the neutrino mass should be less than 0.8 electron volts. That's the best terrestrial result we have at the moment. The cosmological results are, of course, still a bit stronger. Now, we already talked on Monday about Project 8, so I'm not going to go into detail on this any further here. I'd still like to mention briefly neutrinoless double beta decay. Here is once again the process. On the left-hand side, the 2 neutrino double beta decay, where two neutrons convert to 2 protons, each of them emitting an electron and an antineutrino. And here on the right-hand side is the neutrinoless process, where the 2 neutrino lines are connected. So all that's emitted are 2 electrons. And because this is essentially a 2-body decay, the sum of the energies of these 2 electrons is precisely determined. So the experimental signal that one looks for is a peak at this well-known energy. Here's a setup that does this. This is the Gerda experiment in the Gran Sasso lab. There's a lot of shielding around it. And then the actual detectors are these small germanium crystals in here. This is where the actual neutrinoless double beta decays are supposed to happen and where the energy of the outgoing electrons is supposed to be measured. Here's a sketch of the Gran Sasso lab. And this is the result of the experiment. Let me see, do I have only this plot? Yeah, I have this plot only. So let's look in particular here at the bottom part of the spectrum. The top one is just a zoom into the bottom one. The horizontal axis is the energy. The vertical axis is the count rate. You see there's all kinds of background processes. There are a number of nuclear lines that are well understood. And here, where this blue line sits, this is where we would expect an excess if we were observing neutrinoless double beta decay. Zooming into this region up here, we see that there really isn't any excess. Finally, notice that here on the left-hand side, this big red area here, this is the 2 neutrino double beta decay. And even though this looks like a lot of events here, remember that this in itself, it's a very, very rare process. So the fact that the experiment gets so many events, even for an extremely rare process with a lifetime of 10 to the 21 years here, this shows you how incredibly sensitive these detectors are. But well, the rate for neutrinoless double beta decay appears to be even smaller, so there's no signal yet, unfortunately. And here's how this can be translated into a sensitivity on neutrino mass. This plot here shows on the horizontal axis the half-life of xenon-136. That's one isotope that can undergo double beta decay. On the vertical axis, the half-life of germanium-76, another isotope that can undergo double beta decay. The experimental constraints are the horizontal line here and the vertical lines here. And the diagonal lines here are based on different nuclear calculations. So the rate for neutrinoless double beta decay, as we've seen, depends on the neutrino mass, but it also depends on the nuclear matrix element. And these nuclear matrix elements have a huge uncertainty, as you can see in the spread between these colored curves here. And therefore, determining where exactly the constraint on the neutrino mass is highly dependent on the assumptions that are made on the nuclear physics. And so at the moment, the constraint from neutrinoless double beta decay is also somewhere in the EV range. Here, the little numbers here on the diagonal contours indicate neutrino masses in electron volts. I see a question in the chat. Is the 0.8 EV bound for a single mass state or for a mixture of them? That's still a question about KATRIN. It is a constraint on a mixture of them. So I explained on Monday that essentially what KATRIN should be seeing if they had much, much higher precision is they should see the superposition of 3 independent beta decay spectra, one corresponding to emission of nu1, one corresponding to emission of nu2, the other corresponding to emission of nu3. Within the resolution that they have, those 3 spectra still look totally identical. So what they are seeing is a combination of the 3 of them, which is something like the sum over the mixing matrix element modulus squared times m1 plus the next mixing matrix element squared times m2 plus the third mixing matrix element square times m3. So it's a combination of mass eigenstates that they are measuring. But given that the mass differences between the mass eigenstates are tiny as constrained by neutrino oscillations, at this level of sensitivity, we can say that if this combination of mass eigenstates has a mass at 0.8 eV, then each individual one must also have a mass that's very close to those 0.8 eV. So if they were seeing a positive signal at the moment, this would point towards a nearly degenerate neutrino spectrum, where the absolute scale of the 3 neutrino masses is all essentially the same, and there's only tiny differences between the different mass eigenstates.
There's
another question in slide 11. What makes this experiment so sensitive to detect such a rare phenomenon? Well, one of the things that makes it so sensitive is just the fact that it's extremely pure. So they have managed to reduce all the background processes that would normally spoil such a measurement to an incredibly low level. This is achieved on the one hand by going deep underground. As I mentioned, it's installed in the Gran Sasso lab. It's because they have all this shielding around it, right? If you remember this picture here, the whole thing is installed in a clean room. Then around it, there is a water tank, which is instrumented and acts as a muon veto. So when you see a cosmic muon coming in, you cut out the data for a short amount of time in order to reject cosmic ray-induced events. Then around the actual detector, there is liquid argon, which on the one hand absorbs things coming in from the outside, but on the other hand also helps to detect things coming in from the outside. So when a particle is coming into this liquid argon vessel, it can be detected, and once again such events can be vetoed. And then only at the very center are these germanium crystals, and these crystals themselves have also been manufactured to an incredibly high radio purity to avoid all kinds of radioactive contaminants that we would normally have in such materials. And this keeping things so clean, this is really where the art in these experiments lies. This is really where much of the ingenuity is going into. Okay, and I see that Gabriela mentioned that she will be talking about Gödel this afternoon, so perfect. So I should probably shut up because she knows much more about it than I do. Okay, so this is all I wanted to say about neutrino masses. Now let's see, what should we do with the remaining 10 minutes? Would you prefer to hear about the upcoming neutrino oscillation experiments, or shall I talk a little bit about some anomalies that have been observed in neutrino oscillations?
Either is fine.
Either is fine.
We can also have a little more time because we have a large coffee break. So if you want to have 15 minutes, 20 minutes.
Okay, then let me do the following. Let me show you a few slides on oscillation experiments, but not all of them. So let's start. Okay, I want to show this plot because it's a very nice summary of much of neutrino physics. This is a plot that shows where we can get neutrinos from, so where we can take them from to do experiments with them. It's a highly logarithmic plot, both on the horizontal axis that shows the neutrino energy and on the vertical axis, which shows the neutrino flux. It starts out down here at microelectron volt to millielectron volt, with the cosmological neutrino background. That flux is huge, but it's so low in energy that it hasn't been observed yet. And then at higher energies, we go through solar neutrinos, supernova neutrinos, geoneutrinos, reactor neutrinos, atmospheric neutrinos, and then finally high energy astrophysical neutrinos. And somewhere in between here, we would have neutrinos from accelerator experiments. So let me not talk in detail about solar and atmospheric and reactor neutrinos here, but go directly to accelerator neutrinos. So this is a sketch of a typical accelerator neutrino experiment. The plot here is taken from the MINOS experiment, which used to operate at Fermilab for many, many years, but the concept is still the same also in next generation experiments. You always start with a high energy, high intensity beam of protons. That's something that's abundantly available at an accelerator laboratory, and you dump it onto a target. This target is essentially about a meter long rod of, I think, graphite in this case. And what's happening in there is that the protons interact, and in those interactions, they produce lots of secondary particles, most of them pions and a few kaons. Then there is a system called a magnetic horn, and that's essentially a magnetic lens. So it's a magnet with a very special shape that focuses those pions in the forward direction. And that's to make a beam, because you don't want them to splash off in all directions. You want a beam pointed at your detector. So that's achieved by those horns. The pions then travel through a decay pipe. That's basically some empty space that gives them time to decay. And when they decay, they produce each of them produces a neutrino and a muon. The muons are then absorbed, and the neutrinos just go on traveling through the Earth. In the case of the MINOS experiment, they traveled for about 735 kilometers, I believe, until they finally reached the detector. We're going to come to the detector in a moment. Down here, you see a picture of the accelerator, and here you see basically what the neutrino sees. This is a view into the magnetic horn along the beam direction. Okay, so in the end, we of course need to detect neutrinos. So let's talk about two technologies here. Let's talk about water Cerenkov and liquid argon detectors, because those are the ones that are going to be most important in the next generation of experiments. This is a sketch of the Super Kamiokande detector. It's a huge tank filled with water, 50 kilotons of water to be precise, and surrounded on all sides with photomultiplier tubes. It's located deep underground in the Kamioka mine in Japan. So there's more than 1.5 kilometers of rock over it to shield it against cosmic rays, to make sure that we can do neutrino physics in a reasonably background poor environment. So the basic detection principle is that a neutrino comes in, interacts, produces a secondary particle, for instance, an electron or a muon, and that particle is traveling through the water faster than the speed of light. That's possible because remember that the speed of light in water is smaller than the speed of light in vacuum, by about 30% or so, I think. And so since the only fundamental upper limit we have is the speed of light in matter, it's quite possible that a particle travels through material slower than the speed of light in vacuum, but faster than the speed of light in that material. And then what happens is the particle will essentially emit the optical equivalent of a sonic boom. So the acoustic boom that you can hear when an aircraft crosses the sound barrier. Similarly, when a particle crosses the light barrier, it creates a shock wave of light. And this light is then detected by the photomultiplier tube surrounding the detector. Here's a picture of the detector. You see all these photomultiplier tubes around it. And here you see this little rubber boat with people in it that are doing maintenance on the phototubes, and they're all clad in clean room suits, because of course this needs to be very, very clean. Down here, you see a picture of a typical event. This is a view down into the detector. So you can see here the somewhat distorted three-dimensional geometry of the cylindrical detector. And you can see here these ring-like features. Each of them was created by one particle traveling faster than the speed of light in water. And so by reconstructing these rings, we can infer the energy of those particles, and we can reconstruct the event. The other detection technology that's going to be very important in the future is liquid argon detectors. Here is a sketch, and down here are some event displays. A liquid argon detector is essentially a big time projection chamber. So the idea is a particle comes in, a neutrino comes in, produces some secondary particles, and those secondary particles ionize the argon. The charge carriers that are freed in these ionization processes are then drifted across the argon and are then picked up on some wire planes. So in this sketch that is shown here, for instance, these readout planes are here on the top. So the charge carriers are drifted by an electric field upward, and then are picked up in these charge readout planes. And so the arrival time depends on how far they have traveled. So by looking at the time profile of the event, we can reconstruct the spatial profile of the event. That's why it's called a time projection chamber. And here are two pictures of such events. You see here the nice tracks of the secondary particles, pretty clean. So that allows for very, very good event reconstruction. But of course, since argon is more expensive than water, these detectors can't be made quite as big as a detector consisting of water. Okay. Yeah, we already talked about some of these plots, so I'm not going to go through them in detail any further. But I would now like to talk about some oscillation experiments that have happened in the past and that have in fact seen some anomalies. And I would at least like to tell you what the anomalies are. And then it doesn't make too much sense to talk about what the explanation for the anomalies is, because we simply don't know. So let's see. Let me fire up this other presentation. Share screen. Let me, for this, share the whole desktop. Okay. So there are a number of experiments that have observed anomalous signals, but in the interest of time, I'm going to focus on one of them here, which is the mini-boon experiment. Mini-boon is an accelerator-based experiment, so it operates according to the same principle as we've seen just before. There is, on the left-hand side, the thing called booster. Here is one of the accelerators at Fermilab. That's once again a source of a high-intensity beam of protons. They are dumped onto a target, which in this case is embedded inside the magnetic focusing horn. There's again a decay region where the pions and kaons are allowed to decay. And the beam, consisting mostly of neutrinos, then travels through a few hundred meters of dirt until it's picked up by a detector. This detector is essentially a big ball filled with some mineral oil. And in that mineral oil, you get both a scintillation signal and once again a Cerenkov signal. So this is how mini-boon detects neutrinos. So the principle is very, very similar to what we've seen before. The difference is it's an experiment at much, much shorter baseline. So for an experiment targeting standard model oscillations, for these order few hundred MeV neutrinos that mini-boon is seeing, we would need to go to a baseline that's at least a few hundred kilometers. Mini-boon, however, has a baseline of only 1 kilometer. So it's not looking for standard model oscillations, but it's looking for oscillations that have a shorter oscillation length, such as oscillations into hypothetical fourth neutrino state. In fact, this is one of the main purposes why mini-boon was built, in order to test the hypothesis that there are more than 3 neutrino flavors in nature. And the way they are doing this is, as I mentioned, their beam is mostly comprised of neutrinos, and they are looking either for a deficit of those neutrinos, which could arise if some of the neutrinos disappear into some invisible sterile states. And they are also looking for conversion of neutrinos to electron neutrinos, which would not be possible at such short baselines in the standard model. But if there is a sterile neutrino, it means there's a fourth mass eigenstate. So it means there is a third mass squared difference. So we have now delta M21 squared, delta M31 squared, and delta M41 squared. And through this delta M41 squared parameter, now even oscillations among the standard flavors become possible over much shorter distance scales. And that's the effect that Mini-Boon is looking for. Essentially just an additional neutral fermion that would couple to neutrinos through neutrino mixing. Sterile neutrinos, depending on their mass, have lots of other benefits that I won't go into in detail here, but I'm now going to focus on sterile neutrinos with a mass of order an electron volt, so just a little bit above the masses of the active neutrinos. So in that case, indeed, the Mini-Boon anomaly could be explained. The plot here shows on the vertical axis this new mass squared difference between the sterile and active, mostly sterile and mostly active mass eigenstates. And on the horizontal axis, there's an effective mixing angle for this new mu to nu e transitions. And restricted to this parameter space, the red region here, which is favored by all the experimental data we have on this oscillation channel, seems quite consistent. The problem is that this is not the only way we can look for sterile neutrinos. So let me flip through a few slides here because I don't want to talk in detail about the other anomalies that have been observed. I'm just going to tell you that Mini-Boon is not alone in observing an anomaly. So here. So Mini-Boon is looking for these new mu to nu e oscillations. That's the third equation here. Now, in a certain approximation, namely by considering baseline L, which is so large that standard model oscillations, that is so small that standard model oscillations have no time to develop yet, but simultaneously so large that the oscillations between the active and sterile neutrinos are already so fast that we only see their averaged effect. So in this limit, the three oscillation probabilities given here can be written in a quite simple way. So the new mu to nu e probability, the third equation, is the product of two PM&S matrix elements, namely the one giving the mixing between sterile neutrinos and electron neutrinos, and the one giving the mixing between sterile neutrinos and muon neutrinos. The top two channels, electron neutrino survival and muon neutrino survival, depend on only one of those matrix elements. So for instance, if you look at the nu e to nu e channel, you see it's 1 minus a small quantity that accounts for the possible disappearance of electron neutrinos into the sterile neutrinos. So in this very simplified picture, we now have three observables, three oscillation probabilities, depending on only two parameters. So the models can be over-constrained. And this is what these constraints look like. If the anomalies were taken at face value, then the parameters should lie within these red regions. If, on the other hand, the null results, so all the experiments that did not observe any anomalies are considered, then the parameters should lie to the left of the vertex of this black line here. So you see there is a clear tension. There is no region in which the exclusion limits are consistent with the anomalies. So this shows that this hypothesis that there is a fourth neutrino, while it could be invoked to explain individual experiments, it cannot be invoked yet to describe the full global data. And there are, of course, several ways out that people have discussed, either by arguing that maybe those anomalies have a much more mundane explanation. For instance, there are certain challenges with predicting the backgrounds in such experiments. So the question is, could something have gone wrong with those background predictions? People have also developed extended new physics models where maybe the sterile neutrino is not on its own, but maybe shares some interactions with a new scalar or a new gauge boson or so. And all of these solve a certain number of problems and make the global picture more consistent. But I think it's fair to say that at the moment we have the Mini-Boon anomaly, and we have at least three other anomalies that are similarly interesting and that have no explanation yet. And so in that sense, the coming years are going to be quite exciting, both from a theory point of view and from an experiment point of view, because there's now a lot of experiments that are being built or already running to test all these anomalies. So we're for sure going to learn something. Either we're going to discover something fundamentally new, which would be awesome, or we're going to learn something pretty important about, for instance, background predictions. So about how neutrinos interact with matter, for instance, and how that could fool our experiments. And even those lessons, though maybe not quite as glamorous as the detection of a new particle, they will be super duper important, because remember that the community is investing billions of euros into experiments like DUNE and Hyperkamiokande. So when we run these experiments, we should better be sure that our theory is on solid ground and that we understand how backgrounds can be predicted. So with that, I'd like to stop for today. I'd like to thank you for your attention. And of course, I'm still here to answer questions.
Thank you very much, Joachim. Thank you. I would say everyone here on the call should unmute and give Joachim a big round of applause for his 3 excellent lectures.
I see in the chat that Yashwant writes that they'll be talking about the T2K experiment at noon. So there you'll then really get an expert view on a long baseline experiment, and in particular on the super Kamiokande detector. So that will be very exciting. Thanks for pointing us to this, Yashwant.
Yeah. So yeah, this is all, it works together today with all the lectures. So that's great to see this, yeah. So are there any direct questions on Joachim's lecture today? We already had a couple of questions. It was also great that you could give us some glimpse into the future and problems there. So it's a very nice overview. I don't see any immediate question now. Then maybe we can just go for the coffee break on GatherTown. And Joachim, if you have the time to join us, then I guess some students will have the chance also to ask you some questions. Yeah. Thank you very much. And so after, we will leave the Zoom room open, and then at 11:30 we will continue with another talk, another presentation. Thank you very much. See you soon.
Thank you. Thank you, Joachim.
Thanks, everyone.
Bye-bye.
Bye-bye.